Welcome back, Apologia, 8th grade physical science, week 6, day 4, textbook pages 94 to 97, notebook pages 78 through 80. The modern atomic theory. If you recall just a bit of a review here, Rutherford's interpretation of his results with the very deflected alpha particles that he really wasn't expecting. He decided the atom must be mostly empty space, but then it had a concentrated positively charged center that would greatly deflect the alpha particles when they were hit straight on. So his nuclear model explained his results, but like all good science, it also raised further questions. For example, scientists questioned what exactly the electrons were doing in the atom. And if opposites attract, as we know they do, then how did the electrons keep from flying into the nucleus? Well, science was ready for the challenge, and this guy, Niels Bohr, a Danish physicist, continued to develop experiments to test the nuclear model of the atom, which eventually evolved into the electron cloud model. Niels Bohr worked in Rutherford's lab in England and supported Rutherford's nuclear model of the atom. Since Rutherford's model didn't detail how the electrons behaved, other than to suggest that they orbited the nucleus like planets around that concentrated positive center, Bohr decided to focus on electrons and how they were arranged in an atom. Bohr was also interested in what caused the different elements to emit certain colors of light when heated. Think fireworks. Have you ever noticed the different colors of fireworks? Fireworks are made by causing an explosion of substances containing various metal elements. It was discovered that when the element strontium is heated, it produces a red light. When the element barium is heated, it produces a green light. When the element sodium is heated, it produces a yellow light. And when the element copper is heated, a blue light is produced. Bohr was interested in explaining why that happens, and he thought it might have something to do with the electrons. Because of his work with the light-emitting metals, as well as the work done by other scientists such as Max Planck and Albert Einstein, Bohr hypothesized that electrons orbit around the nucleus at fixed distances, like planets orbit around the sun. He reasoned that each electron had a certain amount of energy, and that energy determined the fixed distance of the orbit. Bohr called these fixed distances of the energy levels, or electron shells. These electron shells would circle around the nucleus, which is the center, the positively charged center, one outside of the next, sort of like a sphere within a sphere. So notice figure 319. He further hypothesized that electrons with less energy would be found in lower energy levels closest to the nucleus, and the electrons with more energy would be found in higher levels, farther from the nucleus. So energy levels would increase in the energy they contained from the nucleus outward. So again, this would be the positively charged center. This would be a lower energy level, then it would be a little bit higher, then a little bit higher, then a little bit higher. That's what Bohr hypothesized. He also hypothesized that if an electron absorbed energy, it could jump to a higher energy level. And if the electron lost energy, it would jump down to a lower energy level. The amount of energy gained or lost determined how many energy levels an electron could jump. Also, while electrons could exist in a specific energy level, they could never exist in between two energy levels. So think about it kind of like a ladder. All right, you can stand on any rung on the ladder. Your rungs lower to the ground require less energy of you to actually climb onto them. To climb to the higher rungs requires more energy. Well, with enough energy, you can go up more than one rung at a time. And while you can stand on any rung of the ladder, you cannot ever stand in between the rungs. So Bohr's hypothesis was that electrons can orbit the nucleus only in shells at fixed distances from the nucleus and not in between them. Bohr's hypothesis explained the light he saw when metals were heated. The same colors seen in fireworks. When the explosion in the fireworks heats some of the electrons of the metal atoms, they gain energy. This added energy causes the electrons to move to a higher energy level. In order to move back to their original energy level, the electrons must give off that added energy. Well, some of that energy is released as visible light. Because each element has a unique set of energy levels, different elements emit different colors of light. So the electrons, when heated, get excited and go up an energy level. And when they are ready to come back to their original energy level, they emit a light. Niels Bohr formulated his atomic model in 1913 and actually won the Nobel Prize in Physics in 1922. Bohr's model was the first model of the atom that could account for the known properties of atoms. As you will see in the next module, and you should even expect, by now as science has become more advanced, there have been some changes to this model, not too many. Even so, the Bohr model gives us a reasonably good picture of an atom and is the model you will see most often referred to today. The electron cloud model or the quantum mechanical model. All right, so just as Rutherford improved upon Thomson's model, Bohr improved upon Rutherford's model. Well, Bohr's model was improved as scientists discovered new things about atoms. The electron cloud model is the currently accepted model. Because of the new discoveries, this model of the atom assumes that the movement of electrons is less predictable than those in Bohr's fixed energy levels. In the current model, an electron cloud is used to describe the likely locations for electrons in an atom. All right, so here you see an electron cloud. Scientists call the electron cloud model the quantum mechanical model. This model is very complex because it relies heavily on mathematical probabilities that require post-calculus skills to understand. However, I will try to explain the basic concept to you. Have you ever watched a swarm of starlings or other birds move through the sky? It's really quite mesmerizing to watch. All of the birds seem to move as one unit, but parts of the swarm are moving and twisting much faster than other parts of the swarm. In the densest part of the swarm, you can't really pick out a single bird in any given moment because it is in constant motion. It's a lot like the motion of electrons. Electrons perform a sort of set dance. Some are dancing fast and others are dancing slowly. But each follows mathematical patterns described by an equation discovered by the Austrian physicist Erwin Schrödinger in 1926. Electrons will stay with their pattern dance until they gain energy and speed up, so they dance faster and farther from the nucleus, or they lose energy and slow back down. They would dance slower and closer to the nucleus. No two electrons can occupy the same space at the same time, so comparing that to the swarm of starlings, the birds are moving so fast that what you see looks like a blur. You know there are birds in that blur, but at any specific moment in time, you really can't be exactly sure where a specific bird is. And no two birds can occupy the electron cloud at the same time. Look here at figure 3.22. It is an electron cloud model of a helium atom. Since helium again has an atomic number of 2, we should absolutely know it has 2 protons and 2 electrons. Based on the quantum mechanical or the electron cloud model, each electron is represented by a cloud in the space around the nucleus. We cannot say for certain where the electron is or how it is moving, but we know that the electrons are more likely to be found where the cloud is denser. Here we go. Electron orbitals. All right, according to the electron cloud model, rather than the electrons existing in a fixed orbit, they have fixed amounts of energy that correspond to each level. Because of this, physicists realize that electrons have wave-like properties similar to light waves, as well as properties of particles of matter. It is like these wave-like properties of electrons that keep them at certain distances from the nucleus. Even though the negative electrons are attracted to the positive protons, electrons bend around the nucleus rather than crashing into it because they behave like light waves. I need you to really understand that. Think about this. Think about how light waves bend around obstacles. When you're in a dark room with the door shut, you can still see light coming around that door frame. Sometimes it's enough to see things that are around the door quite clearly. This is because light waves bend, which is called diffraction. Wave behavior also explains why electrons only exist where the wave is stable, which is the rung of the ladder, and not where the wave is not stable, which is between the rungs. Scientists have a name for the stable areas in which each energy level where the electrons are most likely to be found, and we have called those orbitals, which is a region of space around the nucleus where the electrons are most likely to be found. It turns out that there is a limit to how many electrons can exist in each orbital and how many orbitals can exist in each energy level. An orbital can only hold 2 electrons. The first energy level, the one with the lowest amount of energy, only has 1 orbital, so it can never hold more than 2 electrons. That's the maximum. The second energy level has 4 orbitals, and again, an orbital can only hold 2 electrons, so if it has 4 orbitals, the maximum number of electrons for that second energy level is 8. 4 times 2 is 8. The third energy level has 9 orbitals. 9 times 2 is 18, so it can hold up to 18 electrons. The fourth energy level has 16 orbitals, so it can hold up to 32. Again, here we have table 3.2 that lists that out for us. The way electrons are arranged in the orbitals in each energy level is called an atom's electron configuration. An atom has the most stable electron configuration when all of its electrons are in the lowest possible energy levels. Scientists call this stable state the atom's ground state. This is a representation of a sodium atom. It has 2 electrons in the first energy level. So here's the first energy level. It has 1, 2, which we know that's all it can have. 8 electrons in the second energy level. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. And 1 electron in the third energy level. We have 1 electron here. And we know it can have 18. It only has 1. It has filled the first 2 energy levels since they each contain the maximum number of electrons for that level. Now, the electron in the third energy level could absorb enough energy by heating, for example, that it would move to an orbital with higher energy. When that happens, the atom is said to be in an excited state. An excited state is very unstable. And eventually the electron that has jumped to a higher energy level will lose that energy again and return to its ground state. When the electron in sodium returns to its ground state, remember fireworks, the energy is released is seen as yellow light, and that is exactly what happens in fireworks. All right, this completes our discussion on how we know what we do about atoms. On your own, 3.8. When do atoms emit energy as light? We've discussed this now twice. Think back with fireworks. Protons move to a higher energy level. I would hope that you wouldn't think protons at all are on the orbital shells. Electrons move to a higher energy level. Protons move to a lower energy level. Electrons move to a lower energy level. Again, I can hope we can rule out A and C easily. Now, an excited state is when the electrons move to the higher energy level. However, they don't emit the light until they fall back to their lower energy state. So the answer is D. On your own, 3.9, a beryllium atom has 2 electrons in the first energy level and 2 in the second energy level. How do the relative energies of these electrons compare to each other? All right, think about the energy needed to climb up that ladder as a hint to help you with this. The 2 electrons in the second energy level will have more energy than the 2 electrons in the first energy level.